Hi, everybody. This is Mr. Folly, and welcome. Oops, I forgot to do it again. And welcome to our next podcast. I think it's our last podcast for this unit, too. So we will get started and start hopping right to it. All right, molecular polarity. So remember, we already talked about bond polarity, but molecular polarity means a molecule has a positive and a negative end and is determined by two things. Now, these two things are what people get wrong all the time. They forget you need to have both of them. You need to have both bond polarity. Remember, you get that by subtracting the electronegativity values. And if it's 0.41 or more, the bond is polar. If greater electronegativity value is delta negative, we're going to draw the arrow at the bigger En. En is electronegativity. It also needs an asymmetrical shape. This imbalance allows for a positive and negative end. Otherwise, a balanced shape will cancel it out. To identify symmetry, okay? So if it had to identify asymmetry, different outer atoms means it's asymmetrical. Pairs of electrons means it's asymmetrical, unless it's evenly balanced. And imbalance, or the circle trick, which I'll show you in a minute, okay? You need both polar bonds and an asymmetrical shape to be a polar molecule. So let's take a look at these molecules and how it works. Okay, so first of all, the outside are all the same. So that means it could be symmetrical. So I'm going to do my circle trick, which I like the best. Notice this is the 3D shape. So we have the 3D shape that's drawn. And what we have here is the center of my circle is the center of the molecule. So that lands on the same one. So that is symmetrical. So if it's symmetrical, that means it is non-polar. It doesn't matter if the bonds are polar or not. They are, but that's it. See this guy right here? Those are different. Because they're different, that means this is an asymmetrical shape. Remember, symmetry means balance. And see how this has a hydrogen end and this has chlorine ends? That's not balanced, okay? This one right here. See how O is different than F? That tells me it's asymmetrical. And see how I have a lone pair of electrons? I'll draw this over here so I can talk about it. A pair. That means it's asymmetrical. Now, you only need one of those, but I just want to show you some different setups for it. So notice how this would have an oxygen end on top, and then it would have like the fluorine bottom, right? So those would be ended. Remember, polar means ended. All right, so I'm looking right here. My outside atoms are all the same, so I got a shot here, right? I'll do my little circle trick to make sure that it works. Center of my circle is on the central atom. That is symmetrical. If you are symmetrical, you are, oh, I put polar. If you are symmetrical, you are automatically non-polar. So I want to go back to the ones that are asymmetrical. So if you're asymmetrical, what you have to do now is look up the electronegativity values. So I have to take, so for this one right here, I have to take P minus Cl. And P minus Cl on my electronegativity value is greater than 0.40. So it's polar. This guy right here, honestly, when you've got a different atom, you're always going to be polar. So this different atom will always be polar. Okay? And that lone pair and this guy right here will always be polar. Okay? So I'll show you some that are asymmetrical, non-polar here in a second. So this part right here, I've got lone pairs. I'll do my circle trick just so you can see how the circle trick can work the other way. The center of my circle is right here. The X is not on my central atom. So it is asymmetrical. And then electronegativity, the difference in electronegativity of O minus H is greater than, I guess I should just say is greater than 0.40. So it's going to be polar. All right, so we take a look right here. S to F. So if I do my circle trick right here, tight circle, center of my circle is right here. S is not in the center, so asymmetrical shape. Okay, so if I have an asymmetrical shape, then and then F minus S is greater than, oops, I did it again, greater than 0.40. Okay, let me show you one that has an asymmetrical shape. So pH3 circle, middle, so it has an asymmetrical shape, but P minus H is less than 0.4. So because they're not both, that means it's non-polar. So remember, to be polar, you need both. Polar equals both asymmetrical and change. Delta En means changed electronegativity of 0.40 or more. All right, let's keep trucking. Intermolecular forces. So intermolecular forces, there's 3 intermolecular forces. There's hydrogen bonding, which is the strongest. Then there's dipole-dipole, which is middle. And lastly, our wimpy friend dispersion. Okay? So we're going to go through these part by part. Hydrogen bonding is polar molecules, but it needs to have this. It needs to have H bonded directly to N, O, or F. That H is attracted to a lone pair from NO and F from a different molecule. This is a very strong polar bond, so we're going to have dipole-dipole, right? It's a very strong dipole-dipole, but it is a dipole-dipole. So see how this right here? I've got a lone pair on this oxygen, on water, right? So water, if I'm to circle these, we're doing intermolecular forces now, okay? So I'm circling these two. Do you see how that force is between these two? So this bond is very polar, right? So that means this is the very positive end, and this oxygen is very negative. Well, delta, right? And that's where the hydrogen bond occurs, okay? So I'm going to look at this spot right here, and I'm going to add something to make life a little easier. There's a lone pair for nitrogen. There's a lone pair for oxygen. And notice how these different molecules, all right, these different molecules are attracted to each other. Now, a nickel worth of nothing if you can tell me what these molecule is. This is, if I remember correctly, is adenine. Remember adenine, guanine, cytosine, and thymine in DNA? These are two. This is the zip of DNA. Okay. So here, O to H and N to H, again, they have to be different molecules. Okay. That's it. I wish, by the way, these are not touching. It looks like they're touching, but really they're not touching. No touchy touchy. All right. So I wanted to show you one that doesn't have, oh, I'm sorry, I called this not touching. Why is this not hydrogen bond? So let me erase this. All I did was look at the lone pairs on it. So I looked at that and I fell for my own trick. Mr. Foley, you're so crazy. You had such good questions, you trick yourself. Notice how this H is not directly bonded to N or F. And this H is not directly bonded to N or F. No H bonds. H is not bonded. Oh, I just read the word not bonded. Not bonded to my friend nitrogen, my friend oxygen, or my friend fluorine. That's why it's no H bonds, okay? This one is H bonds because I've got a lone pair here, and I've got N to H. And then I got an H bond here, and then my lone pair, okay? All right. So So the strongest force clumps the most. So this means that H bonds clump the most. And we're going to get into what clumpiness means on these properties. There's one other tricky one. This is not H bonding. Just like that other one was not H bonding, because I've got fluorine, I've got hydrogen, but they're not bonded to each other. This is not H bond because it's not direct. All right. So here we go. So that was hydrogen bonding. So hydrogen bonds, as far as intermolecular forces go, pretty darn powerful. So that's good. So let's take a look at not so pretty darn powerful. So we got a medium one. Dipole-dipoles for polar molecules, okay? So nonpolar molecules do not have dipole-dipole. You kind of hear the word polar, kind of makes a little sense. Polar molecule is attracted to another polar molecule, and this is a permanent attraction, okay? The last one is not permanent. H bondings are permanent, these aren't. So I to Cl is a polar bond, right? I've got myself a polar bond right here. This is the negative end, this is the positive end. Well, guess what, boys and girls? Negatives are attracted to positives. Shut up, really? Yeah, I think you knew that already, right? This is stronger than dispersion forces, which is our redheaded stepchild we pay the least amount of attention to down here. And we're going to compare dipoles to other ones. So if I wanted to compare like I to Cl versus O to F, okay, what I would do is I would first look at the difference in electronegativity. Okay, remember, bigger difference in En is stronger. Then I would look at dispersion forces, which is the size of a molecule. So I should tell you this, bigger is more attractive, which is different than what we've done for bond energy, because we're not talking about the difference between them. If it's bigger, it's got a bigger electron cloud, and we'll get into that now. All right, so now we're going to talk about our last bonding type. Our last bonding type is dispersion forces. These are for nonpolar molecules. Everything has dispersion, but this is all nonpolar has. Oh, right? So nonpolar molecule's strongest force. That's all it has. It's not its strongest force, it's its only force. Oh. It is weak. It is temporary, but it can build up. Okay? It's based on the size of the electron cloud. Okay? Bigger molecules have bigger clouds. So let's start with this. If I have an electron cloud and I have 4 electrons, it's probably likely that I'll have 2 electrons on one side and 2 electrons on the other. Okay? But if I have an enormous electron cloud, and say I have 1,000 electrons, okay, one side will probably be something like 490 for an instant, and this side will be 510 for an instant. When that happens, do you see how this side will be just a little bit more negative, and this side will be a little bit more positive? Okay, it could be 500 and 500, but remember, electrons are moving all over the place, and they're all doing that. So the likelihood of them being imbalanced with more of them is much larger, and then you get a temporary charge. So take a look at this. You should be able to draw this. I'm an atom. I had this weird temporary positive and negative. I'm next to it. I am young and impressionable. Here's a positive sign. My electrons say, hey, I smell a positive, and they scoot over there. Does that make sense? All right. So dispersion is the tiebreaker if you're comparing 2 other molecules. Okay. So for example, if I was comparing an H to F bond and an H to N bond, let's say HF and NH3. Okay. So this has a bigger electron cloud, right? So this has more electrons in it. Okay, so does it? Yeah, it does. So this has, nitrogen has 7 electrons plus 3. This one has 9 plus 1. Okay, so I picked a bad example. Let me pick a different one. Let's do H2O. H to O to H. Why do I pick everything that adds up to 10? I'm doing such a poor job. You get an idea for it, so I'm going to stop doing that now. But you're going to pick up ones whichever one has the most electrons. Hard to tell which one is greatest, but clumpier is stronger. So if it's hard to tell when dispersion is greatest, but if it's clumpier, it's stronger. So I'm going to slow down for a second here. How to tell with this? Count electrons. More electrons equals stronger. I was trying to come up with examples off the top of my head, and I kept tying. Okay? Sometimes it's hard to tell when dispersion is greater than dipole or dipole-dipole. So, for example, butter has only dispersion. Butter is a solid. H2O has hydrogen bonds, but it's a liquid. What state of matter clumps together more? Solids do. Butter is stronger for IMF than H2O. So let me put these things in ways that make sense. Okay? All right, so what does it mean to have a stronger force? Well, that means we're going to see some properties that'll be a little different. If you have a stronger force, you're more likely to be a solid like butter than a liquid like water. Okay? It'll have the greatest viscosity. Viscosity is resistance to flow. So if I'm pouring ketchup, it would be very slow. But if I'm pouring gasoline, it pours very quickly. Ketchup has a greater viscosity and greater forces. Okay? The strongest forces have the least evaporation. Evaporation means the liquid particles leave as a gas. Strong forces keep them together. Evaporative things usually smell like gasoline or perfume. If I spill gasoline on the floor, I smell it. And if I spill perfume, I smell it. That means it's evaporating. Okay, but if I spill syrup, you have to clean it up. It won't evaporate away. It has stronger forces. The stronger forces have the most surface tension, held together the most. That means it beads up the most. So this would have a high surface tension, this right here. If I were to draw one with a low surface tension, it would look like this with all of those little circles in there. Okay. Stronger forces would have the higher melting and boiling point. They'd have the lowest volatility. Volatility is the ability to evaporate. Normally, volatility also means that it will catch on fire, but the lowest volatility means it will evaporate the least. And it's very important to know that water has outrageously strong forces for its size. What are those strong forces? H-bonds. All right, recap. This is what you need to have in your soul. Nonpolar molecules have dispersion forces only. That's it. That's all they have. Polar molecules, dipole, or hydrogen bonding. And they also have dispersion. And dispersion. But dispersion is the weakest one, so you don't think about it. So the way to think about this, if I have $100 bills in my wallet, of course I do. Do I worry about how many quarters I have in change? Nope. I got $100 bills, y'all. Woo-hoo. All molecules have dispersion forces. The tiebreaker for dipole-dipole. Polarity. More polar is stronger. That means a bigger difference in electronegativity. The second tiebreaker is size. Bigger is stronger because it would have more dispersion forces. Tiebreakers for all others. If it's bigger, it's stronger because it's more polarizable because it has more electrons. Again, intermolecular forces are between molecules. They are hydrogen bonding, dipole-dipole, and dispersion. Intramolecular forces are within molecules, and for us, it's only covalent for this unit. That's it, to which I will say, toodles.